Having analysed the global air circulation patterns, then the pressure systems, and lastly the surface wind patterns, let's now examine the climate or weather we would expect across the Earth. The global climate will be split into zones, with each zone having unique weather characteristics, which are controlled primarily by the pressure systems found within the immediate vicinity. The first of these zones is found within 10 degrees either side of the equator, and is called the equatorial zone, or the humid tropical zone. This zone is dominated by the passage of the equatorial low pressure belt, or ITCZ. Remember that the ITCZ is characterized by active cloud development and showery precipitation, with cloud developments frequently extending to the tropopause. As we have mentioned, the band of weather will move steadily north into the northern hemisphere from December through to June, and southwards into the southern hemisphere from June to December. The ITCZ will pass through this zone twice during the year, roughly at each equinox. The animation here shows you its passage through this zone. As a result, there will be two main wet seasons. In equatorial East Africa, these rains occur from March to May and are called the long rains, and from November to December and are called the short rains. This zone is characterized by very low annual and diurnal variations of temperature, together with fairly high relative humidities. The next zone is found between 10 degrees and 20 degrees latitude. This is called the savanna. Typically, this zone experiences the passage of the ITCZ only once throughout the year, and as a result, only has one short rainy season in the summer. Look at the savanna in the northern hemisphere and notice when the ITCZ penetrates this zone. The animation will return to the June position to show the ITCZ overlying the zone. The rains will occur in summer, but only for a month or so. For the rest of the time, the dry trade wind from the subtropical highs dominates the weather. This zone is highly dependent on the transitional rains, and if they don't come one year, then the region will experience severe drought with no rain for over a 20-month period. Ethiopia and Sudan are examples of countries found within the savanna zone. The next zone to look at is the one dominated by the large subtropical highs. It is spread from roughly 20 degrees to 35 degrees latitude. This is known as the arid zone. Remember that air is being forced to descend here and will warm adiabatically. Over the land, the cloudless skies will cause surface temperatures to soar during the day and plummet at night. This massive surface diurnal variation and very low relative humidity creates a desert environment. In fact, all of our major deserts are situated within this zone. This huge temperature reduction at night can create very strong nocturnal inversions or radiation inversions. These can be hazardous to aviation, frequently causing wind shear on the approach or departure from airfields within the arid zone. Watching the animation, we can see the transition of the ITCZ and pressure systems. Notice that the ITCZ doesn't fully penetrate this zone, and throughout the year, the subtropical high is still dominating the region. The next zone is called the warm temperate zone, and is a thin band extending from approximately 35 degrees to 40 degrees latitude. Let's just examine the Northern Hemisphere one for now. Notice that in the summer months, in June and July, the subtropical high gives the zone hot, dry, cloudless skies. However, if we continue the animation now to winter, in December and January, then the fringes of the depressions influence the weather here. In winter, therefore, this zone is characterized by cooler, more moist and unsettled weather. This is typical of the Mediterranean and areas of California. The next zone forms part of the temperate latitudes and is called the cool temperate zone. This typically extends from approximately 40 degrees to 65 degrees latitude. This zone is dominated by the travelling polar front depressions and their counterparts, the cold anticyclones or ridges. These move across the globe from west to east. The weather is typically very unsettled throughout the year, but if you look at the animation, it is possible to see that in the summer months, the subtropical highs can penetrate into the lower latitudes of this zone. As a result, the summers can bring warmer, clear spells of weather. Typical areas include the British Isles, where on occasion, the intrusion of the Azores high brings a brief but welcome warm spell in summer. Other areas which have similar weather are New Zealand and the extremes of South Africa and Australia. The last major zone on this model is a polar zone and extends from 65 degrees to 90 degrees latitude. This zone is sometimes referred to as a cold desert. Typically, the air is very dry, but extremely cold. Remember, though, that the polar front depressions are very mobile and do penetrate this zone on occasion, giving very unsettled weather. The effects of the seasons are extreme, where in summer, for a few months, there can be 20 hours of sunlight, but in winter, this can reverse to 20 hours of darkness. However, the effect of the sunshine is very little because of the acute angle of the incoming solar radiation. As a result, even during the summer months, temperatures are rarely above 0 degrees Celsius. The very last zone, which does not truly form part of the model we have constructed, is called the boreal zone. This zone is only found in the Northern Hemisphere, over the land masses of northern North America, Scandinavia, and Russia. It approximately extends from 40 degrees to 60 degrees north. This zone is highly variable, because of the way the large landmass responds to the seasons. In winter, as the land cools, cold anticyclones develop, which generally give cloudless skies and emphasize the cooling effect. Extreme low temperatures can be found especially in northern Siberia, where the temperature can be as low as -60 degrees Celsius. However, during the summer months, the land undergoes warming and the pressure pattern reverses to form gentle low pressures. This zone is characterized by the very high annual variation in temperature, and as an extreme, the highest recorded seasonal temperature change was 105 degrees Celsius in Siberia. Having seen the global aspects of surface wind, pressure and weather, let's now focus on some specific phenomena in a little more detail. Firstly, we will look at the easterly waves. On the map of West Africa, we can see that the ITCZ is well north of the equator, and the Northern Hemisphere is in the summer season. The development of active convective weather along the ITCZ, in particular the Niger Valley, creates groups of thunderstorms which slowly move with the easterly upper airflow. These storms or bands of weather then move off the West African coast into the North Atlantic. Collectively, these movements of active weather are known as easterly waves. About 100 or so of these waves move into the Atlantic each year, and if conditions are right, approximately 1 in 10 of these waves can develop into a North Atlantic hurricane. They can also be observed just north of the equator in South America, and these too may lead to the formation of the hurricanes which are found in the eastern part of the Pacific Ocean. There is another type of weather wave that can be found. These are known as westerly waves, and are typically the waves of weather associated with the passage of the warm and cold fronts of polar front depressions. If you remember, these move across the Earth from west to east, between the latitudes of approximately 40 to 60 degrees. This completes the global climatology lesson. The points mentioned in the lesson and the model that was constructed are vital in understanding how the large-scale weather processes work. This lesson has shown us how the theory we have learnt is brought together to understand the bigger picture of global weather patterns. There are other aspects of global weather which we have already discussed in previous lessons, namely the global upper wind patterns and jet streams. These are also vital and need to be understood in detail to gain the full picture of global climatology.